So in this video, I am going to talk about a limit that doesn't exist. So remember the definition of limit. We say the limit of as x goes to a of f of x is L if for all epsilon greater than 0, there exists delta greater than 0 such that this implies this. But what if there's no number L with this property? If there's no number L that satisfies this, then we say the limit as x goes to a of f of x just does not exist. We proved that if a limit does exist, then it's unique. You can't have two different limits. But it's still possible that you won't have any limit. So if I write a limit like this, either it doesn't exist or it has one single value. So far, all the limits that we've talked about have existed, but today we're going to see one that doesn't exist. So here is the example that I want to talk about. It's the limit as x goes to 0 of f of x, where f of x is this function. It takes the value 1 if x is 1 over n, where n is 1, 2, 3, so n is a positive integer. If x isn't one of those values, then f of x is 0. So just so we all understand the function, I tried to draw a graph. It's a bit hard to draw the full graph, as I'll explain, but for example, f of 1 is 1 because that's one of these numbers, right? If n is 1, then x is 1 over, well, it's 1 over a positive integer. It's 1 over 1, so f of x should be 1. F of a half is also 1 because a half is 1 over a positive integer. F of a third is also 1. So that's why we have these points up here. When x equals 1, when x equals a half, when x equals 1/3, when x equals 1/4, that's this point. And this would keep going. I just kind of tried to draw like a dot, dot, dot here, but that f of 1/5, f of 1/6, f of 1/7 would all be 1. So we'd have all these dots up here. All the other values of x, f of x is just 0. So of course, when you draw a graph, this is always an issue when the graph is on top of the x-axis. But I just tried to make this part darker. And actually, maybe I should make this all darker. Because the value of f of x is 0 here. That's why I'm making this all dark. There's these circles, like there's this open circle here, because f of 1 is not 0, f of 1 is 1. And then there's another open circle here, because that's this one. Okay, so hopefully we all understand the function. So let's prove that the limit doesn't exist. So I need to show that the limit isn't anything. So I'm going to say let L be any real number, and then I'm going to show that the limit is not L. That's what we'll show. So, in other words, I'm negating this. I'm saying the limit is not L. In other words, I'm negating this statement. So how do I negate a statement like this? I have a for all, and there exists, and remember, remember how negating these things works. It changes for all to there exists. So there exists epsilon greater than 0, such that for all delta greater than 0. So I changed this one, and I changed this one, and then I negate the statement inside. Oops. So also a is 0, so 0 less than absolute value of x less than delta does not imply f of x minus L smaller than epsilon. Right. So what does it mean to not imply something here? If you remember, P implies Q means the same thing as Q or not P. So if I'm negating that, that's like negating this. So to negate this, I would say not Q and P. So in other words, let's show there exists an epsilon greater than 0, such that for all delta greater than 0, let's see, this one's P, this one's Q, so I will say not Q, so this is greater than or equal to epsilon, and P. Right, yeah, I don't want to write too close to the edge of the page. I know that's a problem. Right? Right. So, yeah. I just need to show, so starting from the beginning here, I need to show that there exists an epsilon. Here's my intuition. As x approaches 0, I have all these points up here where f of x is taking the value of 1, but I also have all these points down here where f of x is taking the value 0. So whatever my limit is, it's going to have to be close to 1, but it's also going to have to be close to 0, and of course that's going to be a problem. I'm going to take epsilon to be a half, because that's half of the distance between 0 and 1. So let's take that value of epsilon. All I need to do is I need to show there exists a value of epsilon with the properties that I'm looking for. So if I show it for epsilon equals a half, that's good enough. And what else do I have to show? For whatever value of epsilon, I have to show that for all delta greater than 0, I can get this. So I can't choose a specific value of delta. I have to show this for all delta greater than 0. So I'll just let delta be any number greater than 0. Now, I would like to find a value of x satisfying this. So absolute value of x is between 0 and delta. Well, I would like to consider all such values of x, and I would like to consider whether this could possibly be true. So now, among the values of x, such that absolute value of x is between 0 and delta, I'm going to claim I can find one where f of x is 0, and another one, well, maybe I should give these different names. So I can find like an x sub 1 where f of x sub 1 is 0, and one where f of x sub 2 is 1. So why can I do that? Well, maybe let's talk about finding x sub 2 first. So I'd like to find a value of x such that f of x is 1. In other words, I'm just looking for a value of x of this form, like 1 over a positive integer. I can let x sub 2 be 1 over a positive integer, but let's make sure that this value of x sub 2 actually falls in this range. Why are we blurry? Of course, if I'm letting x sub 2 be this, then the absolute value is just leaving it the same because it's a positive number. So if we make sure that, you know, the absolute value of this is between 0 and delta, that's fine, which will be the case as long as, let's see, this number is always greater than 0. This is a positive number, so it's greater than 0. So I don't have to worry about this. To worry about this, I can just solve this for n. Like if I just multiply by n and divide by delta, that should tell me that 1 over delta is less than n. And I can choose a value of n like that. N can be any positive number. 1 over delta, delta is a positive number, but whatever this is just a number, and so I just choose a positive integer that's bigger than that. And I let x2 be 1 over whatever that positive integer is. So that's why I can choose some x sub 2, such that f of x sub 2 would be 1. What should we do for x sub 1? Well, I need to, what I need is a number that isn't of this form, which may be a little bit awkward, but there's a number of things I can do here. What I would like to do is I would like to just say that these are all rational numbers, because this is 1 is an integer and n is an integer. I can just make sure that x1 isn't a rational number. So instead of setting it to 1 over n, I'm going to do the square root of 2 over n. Recall, we proved that the square root of 2 is not rational. So if I take the square root of 2 and I divide it by an integer, that's also not rational. So f of this would be 0, for sure, but we should also make sure that this is in the interval. So, or yeah, I called it an interval, but I'm referring to this. So I should plug x in here and make sure that it's true. So 0 less than root 2 over n less than delta. And again, I'm going to say something similar here. This is a positive number, so it's always greater than 0. And to make this less than delta, I can just solve it for n. So this will be the case as long as, so I move the n over here, I move the delta over here, so root 2 over delta is less than n. And once again, whatever this is just a number. I can choose n to be a positive integer that's larger than that. So what do we have here? Yeah, so let me think about how this is going to go. I have two values of x, both between 0, that both satisfy this, and yet f of one of these values is 0, f of the other value is 1. And so going back to what I was trying to show, I would like to show that, right, one of these is greater than or equal to epsilon. Suppose that neither of these values of x satisfies this. All I have to do is I have to find a single value of x that satisfies this. And I'm going to claim that x1, either x1 works or x2 works. And I'm going to prove this by contradiction. In other words, suppose we don't have this for either value of x. In other words, this is strictly less than epsilon. Then, yeah, so when I plug in x1 for x, f of x1 was 0, so absolute value of, well, I guess it would be absolute value of negative L, but that's the same as absolute value of L, is less than epsilon. And let's keep in mind that we chose epsilon to be 1/2. And also, so this is what I got from plugging in x1. When I plug in x2, remember f of x2 was 1, so that gives me 1 minus L less than epsilon, which is 1/2. Okay, now we're going to use this to get our contradiction. And this is just playing with absolute values and inequalities. So I can use this to say, I can take the absolute values off and put it between 1/2 and minus 1/2. Also, I can do the same here. But let me go ahead and solve this one. This one I would say is solved for L because L's in the middle. Let me do the same for this. So I would subtract 1 everywhere. So negative 3/2 less than negative L less than negative 1/2. And then I'm going to multiply everything by negative 1, which reverses the direction of the inequalities. And if that, yeah, maybe it bothers some people to write it this way, so I can put it in the right direction again. 1/2 less than L less than 3/2. That was just kind of reversing the order. But in any case, we have a contradiction. This is telling me L is less than 1/2. This is telling me L is greater than 1/2. So there can't be any number L that satisfies this. That is a contradiction, and that is the end of the proof.